Hello, this is Dr. D, and I want to look at a couple of binomial probability and distribution problems. Let's take a look at this problem here called taking the train. According to New Jersey Transit, at the 8 a.m. weekday train from Princeton to New York City has a 90% chance of arriving on time on a randomly selected day. Suppose this claim is true and we choose 6 days at random. So this should feel binomial to you because what you're doing here is you have a fixed number of trials. We're going to look at 6 days in total. So n is 6. The probability that the train will arrive on time on any given day is 0.9. And then they have this variable w, which is counting the number of days the train arrives late. So the first question we're asking is, what's the probability the train arrives late on exactly 2 days? All right, so I better be a little bit careful here because the 90% given in the problem is the probability that it arrives on time. And if you look at part A, we're interested in the probability the train arrives late. So for the problem we're doing here, n is still 6. We're still going to try and catch this train 6 days or check 6 days at random. But the probability of the train being late on any of those 6 days would be 0.1, right? The complement of the 0.9. And they wanted to arrive late exactly 2 days. So that's k equals 2. And we have a formula, right? It's the probability that x equals k is n choose k, p to the k, 1 minus p to the n minus k. And so if we plug these things in here, we would get 6c 2.1 to the 2 and 0.9 to the 6 minus 2 or 4. Notice a couple of cool things. For example, these exponents here, the 4 and a 2, add to the number in front. And then also notice that this number here and this number here are the same. This is the probability that the train was late. This is the probability the train was on time. So they should add to 1. Okay, and then we just have to type this into the calculator and get a probability. So here comes a surprise for you. It turns out there's a calculator function that does all this for you. You do need to know the formula though, which is why we did it. So let's take a look here in the calculator. And let me just minimize, shrink this a little bit for you. There we go. That's a little bit better. Let's do second quit. Go to the home screen. And what we do is we're going to do second distributions again, like we would go and get normal CDF. However, if you go down far enough, you'll find something, letter A, says binomial PDF, and that's the one you want when you have a probability of like exactly x equals 2. Just put a picture of that into the notes for us. So we have it. Okay, so here we go. I'm going to select that. It's going to say trials. That's n, which is 6 in our case. P, probability the train is late, 0.1. And the x value was 2. If I hit paste and enter, then I get that probability, which is exactly what I would have gotten had I taken the time to type all that in. So we just look at that number again. What was it? 0.098. So that's what this is, 0.098. That's the answer to part A, 0.098. Okay, let's look at part B. You can see they're asking us to find the probability that W is greater than or equal to 2 out of 6. So let's take a look at that. Probability that W is greater than or equal to 2 will equal probability that W equals 2 plus probability that W equals 3 plus all the way up to probability W equals 6. And if we think about it from a formula point of view, what we'd have to do is, we'd have to do this case, we'd have to do like, let's see, 6 choose 2, 0.1 to the 2, 0.9 to the 4, plus the next one, which would be 6 choose 3, 0.1 to the 3, 0.9 to the 3, plus dot, dot, dot. And finally, at the end, you get 6 choose 6. And you'd have 0.1 to the 6 and 0.9 to the 0. So it turns out there's a faster way to do this also. Your calculator has a button in it called Binomial. Let me show you. CDF. So notice I'm not saying PDF, CDF. So I do second distributions, and I go, well, let's go up here. Letter B says Binomial CDF. That stands for Cumulative Density Function. So if I select that, it looks like all the same things, trials, probability, all that stuff. What the CDF does is, the binomial CDF, it computes the probability that x is less than or equal to whatever number you choose. So that's a little bit of a problem for us because we wanted the probability that w was greater or equal to 2. And so the problem with that, of course, is CDF, this new function I told you about, doesn't do that. It does less than or equal to. So what we do is we're going to change this to the opposite event. So the opposite of something being greater than or equal to 2 is that that thing is less than 2. So that's what we have here. Okay, so that turns out to be the key step. So again, greater than or equal to, the opposite event of that, so I'm doing 1 minus, is less than 2. Now it's still a problem for us because the calculator only does less than or equal to. Okay, so we're going to change this one more time. We're going to say this is equal to 1 minus the probability that W is less than or equal to 1, right? Less than 2 trains being late means 1 or less trains being late. I'll say that again. If you want less than 2 trains to be late, that means you have 1 or 0 trains that are late. So we can actually do this right in the calculator now. We're going to do 1 minus the binomial CDF, 6 trains, probably the latest 0.1, and then we're going to put a 1 here. So let me show you how to do that. So let's go in the calculator here. So we're going to have 6, 0.1, and 1. We're going to hit paste. There it is. The only thing I need is a 1 minus. So I'm going to put that in front. I'm going to insert that 1 minus. There we are. And if I hit enter, that's the probability that 2 or more trains are late. Okay, so 0.114 is the answer to the second question. Okay, a couple more things you could actually ask about. I could ask you to create a graph of a probability distribution for a problem. So let's talk about how we do that. So in our calculators here, what we need to do is make a probability distribution first. So here's how we do that. We're going to go to Stat, and we're going to go to Edit. All right, you may have some stuff in here, so remember, go to the top of the list and hit Clear to get rid of whatever you have there. Don't overwrite it. Sometimes you end up with an issue. So here we go. If we're talking about seeing what happens with the train showing up late, forgive me, on 6 days, then maybe it doesn't show up late any of the days. So maybe 0 is a possible value of W. Maybe it shows it late only once, or maybe 2 times, or maybe it ends up being late on all the days. Okay. So these are the possible values of W. Okay. What I need next is I need the probability of each of those values. So if you go to the top of list 2, here comes the clever part. I think you're going to like this. So I want the probability, for example, and here I want to have the probability that no trains are late. Then I'll have the probability underneath that exactly 1 train is late. That's what's going to go underneath that and so forth. So watch, let's do this. Second distributions. I'm going to go find that binomial PDF button. The trials are 6. Probability the train is late is 0.1. And the X value, here's the clever part, second 1 is in list 1. So I'm going to hit paste now. And there it is. So it's going to change the X value or the W value as we go along. So I hit enter now, I'm going to get every probability for every situation. Okay, so this thing we have here, this thing that we just created, that's called the probability distribution. And what I want to do is make a histogram out of that. So here's how we do it. We go second y equals, second stat plot. We hit enter. We're going to turn this graph on. And then we're going to go to type. And we're going to go over and select this right here, which is a histogram. Okay. And then here's where we got to be careful. So my X values are actually in list 1. That's the 0, 1, 2, 3 up to 6. the frequencies are the probabilities of those numbers, and those numbers are in list 2. So that's something we haven't really done too often when it comes to histograms. So you have to be real careful with that. Okay. Once you've done all this, just do second quit to get out of there, and now your stat plot is set up. We need to actually graph it, so we're going to press zoom, and I'll always ask you, hey, which zoom looks good? And if you look down far enough here, if we go down here, number 9, zoom stat. Okay, so I'm going to tell you in advance right now, unfortunately, this is not going to work well. So let's hit enter, and we get just, looks like 1 bar. And that doesn't really make a lot of sense because the numbers we had were 0, 1, 2, 3, up to 6. You would have expected 6 bars. So something's wrong. So we always have to fix these windows. We've talked about this before. Press the window button next to y equals the button that says window. It makes sense that x min is 0 because 0 is the smallest value of x. And then here's a general rule for x max. Be very careful. We always go 1 bigger than our highest value of x. Our highest value of x in this case, or w I should say, was 6. So we're going to go to 7. And here comes the most important step, the x scale. The x scale determines the width of the bars. So you'll notice in this case, x scale somehow got set to 6. Zoom 9 didn't do a good job for us. But we know that we want our bars to have width 1. I'm going to press 1. All right, let's see what happens. So what we do now is press graph, and we can see some of our bars. It's not perfect, but this graph's a little higher than it needs to be. I'm noticing Y max is pretty big, so let's go back to window. Let's change Y max to, let's try like 0.6 or 0.5. I don't think it needs to be much bigger than that. Let's press graph, and you can see a little bit more here. You've got a sense of the histogram. Just putting that into the notes there. If you press the trace button next to graph, what you'll see is the height and what happens in each situation. And you can see these other bars actually have heights. They're just so small. You can barely see them. So you can tell here, this is saying that it's really unlikely for all 6 trains to be late. That sort of makes sense. Okay. Another question you might ask is, how often do we expect a train to be late? And what kind of variability do you expect? So that means, can we find the mean and the standard deviation? And the answer is yes. So now there's really 2 ways to do it, and you're responsible for both. It turns out there are formulas for the mean and standard deviation in the binomial setting. So here's what they look like. Ready? So the mean is equal to n times p, or in our case, it would be 6 trains times 0.1, which would be 0.6. Now, I don't know about you, but I think this formula makes sense. If we know that 0.1 or 10% of the trains are going to be late, and then I observe 6 trains at random, I would expect 10% of those 6 trains to be late. So that's where the 0.6 is coming from. Okay, standard deviation is not obvious. Here's the formula for it. It's the square root of n times p times 1 minus p, or in our case, it would be the square root of 6 times 0.1 times 0.9. All right, let's go type that in the calculator for a second. So let's do second quit, square root, 6 times 0.1 times 0.9, enter, and I get 0.734. So that's the typical variation from the mean. That, yeah, we'll just say it that way. Okay, so that's the mean and standard deviation. Now, the formulas are nice. You do need to know them. So they're given to you on the reference sheet, of course, for the AP exam, but we still need to recognize them. Interestingly, because in this particular problem, we went to the trouble of actually putting all the x values in list 1 and all the probabilities in list 2, we could actually do this. We can go stat, calc, 1 variable statistics, second 1, enter, second 2, enter, right? Hit calculate, and you should recognize some numbers here. Let me just put it into notes for us, and then we'll highlight those. Ready? So look, there's our mean, and that came from the formula we had a moment ago here. You can see it right there. And there's our standard deviation, which came from the formula over here. Okay, So now you know how to do all the things related to the binomial setting. Um, this is a problem I'd like you to try. So you can just pause the video and give this problem a try and see what you come up with. And then when you're ready, you can restart the video and do this problem. Okay, so if we look here, the companies, this is seed depot, the probability that a seed germinates is 0.85. And then they tell us that we're going to take 20 packets. So it looks like n is equal to 20. And in this first case, we want the probability at exactly 17, probably x equals 17. So we can use our formula if we want, or we can use our new binomial PDF button. So let's do that. Second distributions, go up or down to binomial PDF. N was 20 in this case. The probability a seed germinates is 0.85. And the x value is 17. Hit paste and enter. And we're getting 0.24, right? So this is 0.24 about. Yep, that all looks good. The second question is really interesting. What if only 12 seeds germinated? Would you be suspicious that 85% of the company's seeds actually germinate? And they tell us to calculate this probability. So this actually turns out to be a super important question. We're combining what we just learned about binomial PDFs and CDFs with some statistical reasoning. I'm just going to highlight this just to make a big deal out of it. A question like this is super important to understand. Okay, anyway, you can just do the following. So this is going to be a binomial CDF, right? Because it's less than or equal to. We're examining 20 seeds. The probability any particular seed germinates, forgive me, is 0.85, and we want 12 or less. So luckily the calculator does this kind of thing for us directly. There'll be no 1 minus tricks or anything like that this time. So let's go do that. Second distributions, binomial CDF. Here we go. 20 trials, 0.85, and 12. And we've got a probability of 0.005. 0.006 really about. Okay. So the thing for you to notice is, to answer this question we've highlighted in yellow, is that probability is extremely small. Extremely small. It's very unlikely to have less than or equal to 12 seeds germinate. So the question is, what should that tell you about the company's claim? The company claims 85% of their seeds germinate. We found the likelihood that only 12 or less would germinate, and we realize it's extremely small. So we should not observe this, and that means we should be suspicious of the company's claim. We should think that the company's claim is not true. That idea we just talked about is called statistical inference. It's a tough question. Okay. Let's go. We could do a couple other things here. We can create a probability graph of this distribution. We'll do that in a second, and we can also find the mean and standard deviation. Let's just do that real quick. It's going to be n times p. So there were 20 seeds, and 0.85, 85% of them germinate. Okay, so if we do the math on that, 17, not surprising, I guess. Standard deviation is the square root of np 1 minus p. In our case, the square root of 20 times 0.85 times 0.15. Okay, and if we go over here, let's do that. Second square root, 20 times 0.85 times 0.15. Enter. And standard deviation about 1.59. Okay. This number here, maybe let's just think about that one more time. I was claiming earlier that I think this formula makes sense. If we're going to inspect 20 seeds and we expect 85% of them to germinate, then we'd expect 85% of the 20 seeds we looked at to germinate. So that's where the 17 is coming from. Okay, makes sense. Let's just quick make a histogram out of the situation, and then we're done. So let's take a look. Remember, n in this case is 20. The P probability is 0.85. And then K, the number of successes we could have. Maybe none of the seeds germinate. Maybe one germinates. Maybe two germinate. Maybe 18, 19, 20. So these are all the possible values that we could have, right? So let's go to our graph here. Let's go to Stat. Let's go to Edit. And I'm going to clear out list 2. And list 1 actually has got a good start for us, but we need more numbers now. We need to get all the way to 20. So we're going to have 7, 8, 9. So this will take us a while to type, but I'm going to do that now. Take your time. Make sure you don't make any errors. Speed up the video if this is too boring. And that's 20. And then this window, this column looks scary, but it's actually going to be easy. We're going to go to the top of list 2. We're going to do second distributions. We're going to go to the binomial PDF. Trials are 20. Probability C germinates is 0.85. And the X values are in list 1. And there we go. So watch how fast that list 2 is going to populate. And there we go. Is all our probabilities. You should notice these numbers are really small. That's because n is just so big. And all these probabilities have to add to 1, so we've broken them all into very small pieces. Let's create the graph. So we go to stat plot. And then amazingly, this graph's already set up because same thing, list 1, list 2. There's nothing special about this setup. We know if we press zoom 9, it's not going to be good. So let's be a little smarter about it this time. Let's go back to stat edit for a moment. And I'm just going to look down list 1. And if I look at all these probabilities, the biggest one I see is a 0.18, 0.24. Oh, wow. So there's no probability bigger than 0.25. So I'm going to go to window now. And my X min should be 0. My X max should be 21 because it's 1 bigger than the biggest number. The X scale should be 1. And here's where we're going to be clever. For my Y max, I'm just going to make it 0.25 because there was no probability bigger than that. So let's press graph and see what we get. Yeah, you kind of get a sense of what this graph looks like. Notice these two graphs, when we think about the two graphs we created today, right? This one here looks like it's skewed left, right? It's like that. And notice the probability we had, P, was 0.85. Okay. And go back to the earlier problem in this question. This graph is skewed right. And notice in this problem, the probability, if you remember, was 0.1. So it turns out binomial distributions will be skewed. And with the following rule, actually, if you think about it, this probability here is less than 0.5. And so we ended up with a skewed right graph. This probability was greater than 0.5. We ended up with a skewed left graph. So final summary here. If P is less than 0.5, then like we saw earlier, the graph is skewed right. So I'll just say skewed right. If P is greater than 0.5, we expect the graph to be skewed left. And if P equals 0.5, we expect the graph to be symmetric. Okay, so this is the lesson for today. Make sure you watch and do everything you need. There'll be a set of problems on Canvas for you. Thanks for watching, and it was a pleasure.